We must find Sean's total earnings for each of our contract options, Contract A and Contract B. His total earnings can be found by adding together his basic salary to the commission he makes on his sales. In Contract A, the base salary is €35,000. To find his commission, we'll multiply together his total sales by the percentage commission he receives. Here, the total sales are €400,000 and the percentage commission for Contract A is 2%. To make things easier for our calculator, we should convert this percentage to decimal form. We do this by dividing by 100, so 2% will be 0.02 in decimal form. When we perform our calculation, we get an answer of €8,000 for our commission. To find our total earnings, we'll add our salary to the commission, so we get 35,000 plus 8,000, which is 43,000. A similar approach can be used to find the total earnings for Contract B. Here, the base salary is €30,000. Again, our commission is found by multiplying total sales by the percentage commission. Our total sales is still 400,000, but for Contract B, the percentage commission is 3%. Rewriting in decimal form, the calculation will become 400,000 times 0.03. When we do this, we get €12,000 for our commission. To find our total earnings, we add together the salary of 30,000 to the commission of 12,000, and this brings us to 42,000. The total earnings for an employee can be found by adding together their base salary to their commission. Mary has total earnings of 50,000. Since she's on Contract A, her basic salary is 35,000. Since earnings are equal to salary plus commission, we'll have 50,000 equal to 35,000 plus her commission. Subtracting 35,000 from both sides tells us that she must have made €15,000 in commissions. So, how can we use this to find our total sales? Well, commission is calculated by multiplying together total sales times the percentage commission on those sales. We know our commission is 15,000, and since Mary is on Contract A, her percentage commission is 2%. To make things easier for our calculator, I'll convert this percentage to decimal form. Dividing by 100, we can rewrite 2% as 0.02. We want to know our total sales. This appears on the right-hand side of our equation, but is being multiplied by a number, 0.02. To get rid of this multiplication, we should perform the inverse operation. The opposite of multiplication is division, so to get rid of multiplication by 0.02, I'll divide both sides by 0.02. From here, it's just some calculator work. Performing the calculation on the left-hand side gives us a final answer of 750,000 sales. We have two contract options, Contract A and Contract B. We want to find the number of sales which leads to equal earnings in both of these contracts. In other words, we want our Contract A earnings to be equal to our Contract B earnings. To find our Contract A earnings, we add together the base salary to the commission. The base salary is 35,000 and the commission is 2% of whatever sales were made. Rewriting the 2% as a decimal, this becomes 35,000 plus 0.02 times the sales. The earnings from contract B will be the base salary of 30,000 plus 3% of any sales made. Rewriting our percentage as a decimal, this becomes 30,000 plus 0.03 times the sales. Since we want the contract A earnings to be equal to the contract B earnings, we'll set these expressions equal to each other. The goal here is to find the number of sales. There's a bit of an issue, which is that sales appears more than once in the equation, once on the left and once on the right. The strategy here will be to group together these sales terms on one side and then group together all the number terms on the other side. Let's group the number terms on the left and the sales terms on the right. To begin, we can remove the 30,000 from the right-hand side by subtracting 30,000 from both sides. Next, to remove the 0.02 sales from the left, we can subtract this term from both sides. Now we can do some simplification. 35,000 minus 30,000 is 5,000. And 0.03 times sales minus 0.02 times sales gives us 0.01 times sales. We want to isolate our sales. Here, it's being multiplied by 0.01. Since the opposite of multiplication is division, to get rid of this, we'll divide both sides by 0.01. Performing the calculation on the left-hand side gives us our final answer that the sales is equal to €500,000. Complex numbers have two components, a real component and an imaginary component. To plot a complex number, we just need to identify what these two components are. Z1 is equal to minus 2 plus 3i. Here, the real component is a number by itself, the minus 2. The imaginary component is a number in front of the I. Here, that's plus 3. So to plot our point, we go to minus 2 on our horizontal real axis, and we go to plus 3 on our vertical imaginary axis, and plot a point right here. Z2 is equal to minus 3 minus 2i. Here, the real component is minus 3, and the imaginary component is minus 2. So we go to minus 3 on our real axis, minus 2 on our imaginary axis, and plot a point right there. Z3 is equal to Z1 minus Z2. Before we can plot this, we must calculate what this actually is. So let's write in the values of Z1 and Z2. We have to be careful with our signs here. We're subtracting Z2, which is minus 3 minus 2i. Minus minus 3 gives us plus 3, and minus minus 2i gives us plus 2i. From here, we can combine our real parts and the imaginary parts. Minus 2 plus 3 is 1, and 3i plus 2i is 5i. We are now in a position to plot Z3. The real component is 1, and the imaginary component is 5, so our point will go right here. This question involves the modulus of a complex number, so it's important that we know how to calculate this. If we have a complex number z, which is equal to a plus bi, then the modulus of z is equal to the square root of a squared plus b squared. The equation we're given has three moduluses in it: the modulus of z3, modulus of z1, and modulus of z2. So let's go ahead and calculate each of these. In part A, we found that z3 is equal to 1 plus 5i. So we have a real component of 1 and an imaginary component of 5. To find our modulus, we square each of these and add them together, and then put the result under a square root. 1 squared is 1, and 5 squared is 25, so we end up with the square root of 26. We can type this in our calculator to convert it to decimal form, and we'll get 5.099. So we found the modulus of z3. Let's do the same thing for z1 and z2. z1 is equal to minus 2 plus 3i. The modulus will be minus 2 squared plus 3 squared, all under a square root. Minus 2 squared is 4, and 3 squared is 9, so we end up with the square root of 13. Converting to decimal gives us 3.606. z2 is minus 3 minus 2i, so our modulus is minus 3 squared plus minus 2 squared, all under a square root. This simplifies to the square root of 9 plus 4, which is equal to the square root of 13, and if we type this in our calculator, we can convert it to decimal form, and we'll get 3.606. We now have all the information we need to investigate our statement. On the left-hand side, we know that the modulus of z3 is equal to 5.099. On the right-hand side, we have the modulus of z1 plus the modulus of z2. We know what both of these are, so let's add them together. The calculation here comes out at 7.212. So, are the two sides of this equation equal? Well, the answer is no. 5.099 is not equal to 7.212. So it is not the case that the modulus of z3 is equal to the modulus of z1 plus the modulus of z2. We must calculate z4, which is equal to z1 divided by z2. We know what z1 and z2 are, so let's write these expressions in. We're trying to divide complex numbers here. To tackle this, there's a bit of theory we need to know. To divide complex numbers, we should multiply above and below the line by the conjugate of the denominator. So how do we find the conjugate of a complex number? Well, this is obtained by changing the sign of the I part. For example, if we had 4 plus 3i, the conjugate would be 4 minus 3i. If we had 2 minus 6i, the conjugate would be 2 plus 6i. The denominator of our fraction is minus 3 minus 2i. The conjugate here would be minus 3 plus 2i. So the strategy here will be to multiply above and below the line in our fraction by minus 3 plus 2i. From here, we can multiply out our brackets. Let's try to simplify our expression. An important fact in complex numbers is that I squared is equal to minus 1. So the I squareds can be replaced with minus 1. Now let's simplify some more. In the numerator, minus 4i minus 9i is minus 13i, and 6 by minus 1 is minus 6. In the denominator, the minus 6i and the plus 6i cancel each other out, and minus 4 times minus 1 is plus 4. Simplifying further, the 6 and the minus 6 cancel out in the numerator, and 9 plus 4 becomes 13 in the denominator. From here, minus 13i divided by 13 simplifies to minus I. We are asked to present our answer in the form x plus yi. In other words, we want a real component x and an imaginary component y. To do this, we can rewrite our minus I as 0 minus 1i. The equation we are given involves an x squared term, an x term, and a number term. This is referred to as a quadratic equation, and to solve it, we can use the quadratic formula, which is on page 20 of our formula book. It says that the roots of the quadratic ax squared plus bx plus c equal to 0 are x is minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. To use this formula, we should begin by identifying the values of a, b, and c. A is the number in front of the x squared, and here a is equal to 2. B is equal to the number in front of the x, and here b is equal to minus 7. C is the number by itself, and in our equation we'll have c equal to minus 3. Now let's sub these values into our formula. Let's simplify a bit. Minus 7 is plus 7, minus 7 squared is 49, and minus 4 times 2 times minus 3 is plus 24. In the denominator, 2 by 2 is just 4. We can simplify further by adding the numbers under the square root. 49 plus 24 is 73. So, how do we deal with this plus minus sign? Well, this means we should split into two cases. In the first case, we replace this symbol with a plus, and in the second case, we replace this symbol with a minus. From here, it's just going to be some calculator work and some rounding. Using our calculator, the first expression comes out as 3.886001. Since we are asked to give our answers correct to 2 decimal places, we can round this off to 3.89. Using our calculator, the second answer comes out as minus 0.386001. Rounding to 2 decimal places gives us minus 0.39. We can solve these simultaneous equations using elimination. The strategy is to make one of the numbers match but with different signs. Here, I'll focus on the numbers in front of our b term. In our first equation, the number in front of the b is plus 3. So what we'll want in the second equation is the same number, 3, but the different sign, so minus 3. So we want a minus 3 in front of the b in the second equation. This can be obtained if we multiply across our second equation by minus 3. 5a times minus 3 is minus 15a, plus b times minus 3 is minus 3b, and minus 8 times minus 3 is plus 24. We now have the match on the b term that we wanted. We've the same number, 3, but different signs. The next step will be to add our equations together. 2a minus 15a is minus 13a. The plus 3b and the minus 3b cancel each other off and give us 0. And 15 plus 24 is 39. So now we have an equation in a, minus 13a equals 39. To find a, we'll need to get rid of this minus 13. This is being multiplied by the a, so to get rid of it, we should do the inverse operation to both sides. In other words, we should divide both sides by minus 13. Performing the calculation on the right-hand side gives us an answer of a is equal to minus 3. We're not done yet. We were asked for the value of b as well as the value of a. To find this, we can take one of our original equations and substitute in the value of a we found. Here, I'm going to take the first equation, 2a plus 3b equals 15. We found that a is minus 3, so we can sub this in. 2 times minus 3 is minus 6, so we get minus 6 plus 3b is 15. The goal is to find what b is, in other words, to get b all by itself on one side of the equation. To do this, we'll want to get rid of the minus 6 and the 3. The minus 6 represents subtraction, so to get rid of it, we do the opposite, addition. So here, we'll add 6 to both sides. We can simplify the right-hand side here. 15 plus 6 is 21. The 3 in front of the b represents multiplication, so to get rid of it, we do the opposite, which is division. So here, we'll divide both sides by 3. 21 divided by 3 is 7, so we get our answer that b is equal to 7. Let's try to spot the pattern. To start, let's focus on the grey tiles. In stage 1, the grey tiles form a 2 by 2 square. In stage 2, the grey tiles form a 3 by 3 square. In stage 3, the grey tiles form a 4 by 4 square. So the pattern here is that the grey tiles form a square, and the length of the square increases by 1 in each stage. In stage 4, we'd have the grey tiles forming a 5 by 5 square. Now let's focus on the white tiles. In each of the first 3 stages, we have 2 white tiles. One of them juts out horizontally from the bottom right corner, and the other juts out vertically from the top right corner. Adding in white squares in these positions finishes off the pattern for stage 4. We have the first 4 patterns drawn out, so we can use this as a guide when we're counting up the number of tiles. Let's begin by focusing on the number of grey tiles. In stage 1, the grey tiles form a 2x2 square, which gives us 4 grey tiles. In stage 2, the grey tiles form a 3x3 square. This gives us 3 times 3 equals 9 grey tiles. In stage 3, we have a 4x4 square, which gives us 4 times 4 equals 16 grey tiles. For stage 4, we have a 5x5 square, and this gives us 5 times 5 is 25. Even though we don't have stage 5 drawn, we can continue the pattern. In stage 5, we'd have a 6x6 square, which gives us 6 times 6 is 36 grey tiles. Focusing on the number of white tiles, we can observe that each stage has exactly 2 white tiles, one jutting out from the bottom right and one jutting out from the top right. So we'll have 2 white tiles in each of our stages. To find the total number of tiles, we just need to add together the number of grey tiles to the number of white tiles. 9 plus 2 is 11, 16 plus 2 is 18, 25 plus 2 is 27, and 36 plus 2 is 38. In this question, we need to find a formula for Tn, the total tiles in stage n. To do this, we can generalise the pattern from the table we made out in part B. In other words, we can think about the number of grey tiles and number of white tiles in row n of our table. For stage 2, the number of grey tiles was 3 times 3. For stage 3, it was 4 times 4. For stage 4, it was 5 times 5. And for stage 5, it was 6 times 6. The pattern here is that the number we're multiplying by itself is 1 bigger than the stage. So for stage n, the number of grey tiles would be n plus 1 times n plus 1. The number of white tiles is a bit easier. It's 2 in every single stage, so there'll be 2 white tiles in stage n. The total number of tiles can be found by adding these two numbers together. So, we found an expression for the total tiles in stage n. It's n plus 1 times n plus 1 plus 2. We want our answer in the form n squared plus bn plus c, so here we should expand out our brackets. N times n is n squared, n times 1 is n, 1 times n is n, and 1 times 1 is 1. From here we can simplify a bit. N plus n is 2n, and 1 plus 2 is 3. Now, our expression matches the target of n squared plus bn plus c. B is the number in front of the n, so here b is equal to 2. C is the number by itself, and here c is equal to 3. In part C, we worked with an expression, Tn, which represented the total tiles in stage n. We want to have 443 total tiles, so we should set Tn equal to 443. In part C, we found an expression for Tn. It was equal to n plus 1 times n plus 1 plus 2. We can write this expression in the place of Tn and then solve the resulting equation for n. As a first step, we can rewrite the n plus 1 times n plus 1 as n plus 1 all squared. to remove the 2 from the left-hand side, I'll subtract 2 from both sides. We want to isolate n, so we'll need to get rid of the +1 and the square. Let's start by removing the square. The inverse of a square is a square root, so here I will square root both sides of my equation. The square root cancels the square, so we end up with n plus 1 equal to the root of 441. Doing some calculator work, this simplifies to n plus 1 is equal to 21. As our final step, we can get rid of the +1 by subtracting 1 from both sides. This brings us to a final answer of n equal to 20. So the 20th stage of our pattern will have 443 tiles. The coordinates of a point come in a pair of two numbers, a horizontal x component and a vertical y component. Point A has a horizontal x value of 0 and a vertical y value of 6. So the coordinates are 0, 6. Point B has a horizontal x value of -2 and a vertical y value of 0. So the coordinates are -2, 0. C has a horizontal x component of 3 and a vertical y component of 0, so the coordinates are 3, 0. There is a useful fact about quadratics which will help us here. If a quadratic, f of x, has roots r1 and r2, then f of x is equal to x minus r1 times x minus r2, or f of x is equal to minus x minus r1 times x minus r2. The only difference between these two options is the minus sign. The first case is for happy face quadratics, where the function shoots upwards in both directions. The second case is for sad face quadratics, which goes downwards in both directions. Since our function resembles a sad face, we will use the second option. F of x is equal to minus x minus r1 times x minus r2. The roots of the quadratic are the locations where the graph crosses the x-axis. In our function, the roots are -2 and 3. So these are the values for r1 and r2. Let's sub these values into the expression we had. We can simplify by noting that minus -2 is the same as +2. Now we can multiply out our brackets. X times x is x squared. X times -3 is -3x. +2 times x is +2x. And +2 times -3 is -6. Now we can clean things up a bit. -3x plus 2x is -x. To finish off, let's deal with this minus sign outside our brackets. This has the effect of changing the signs of each of the terms inside. So we get -x squared plus x plus 6. And now we're done, since this is precisely the expression we were asked to come up with. Finding the minimum or maximum point of a function involves a few steps. First, we differentiate the function. Then, we set the derivative equal to 0 and solve. And finally, we'll sub back into the original function. From part B, we know that we can write our function as f of x is equal to minus x squared plus x plus 6. To begin, we'll need to differentiate this. Whenever we are adding or subtracting terms, we can differentiate each term individually. So we can tackle the minus x squared, the x, and the 6 separately. Let's start with the minus x squared. We have a rule for differentiating powers of x, which says, multiply down by the power, then reduce the power by 1. The power here is 2, so we multiply down by 2, and then reduce the power from 2 to 1. This gives us minus 2x. To differentiate the x, we can use a rule which says that for any constant k, k times x differentiates to k. We have x, which can be thought of as 1x, so this will just differentiate to 1. Finally, let's deal with the plus 6. There's a rule which says that additive constants simply differentiate to 0. In other words, they disappear. So differentiating the 6 makes it disappear. We're now on to step 2. Set the derivative equal to 0 and solve. We found that the derivative is minus 2x plus 1, so let's set this equal to 0 in an equation. To solve for x, we need to isolate it all by itself on one side of the equation. To do this, we'll need to get rid of the minus 2 in front of it and the plus 1. Let's start by removing the plus 1. This represents addition, so to get rid of it, we should subtract 1 from both sides. The minus 2 in front of the x represents multiplication, so to get rid of it, we should do the opposite. We should divide both sides by minus 2. Calculating our right-hand side, we get our answer that x is equal to 0.5. We've now found the correct x-coordinate for our point. To find the y-coordinate, we'll need to sub back into the original function f of x is equal to minus x squared plus x plus 6. Since x is equal to 0.5, let's replace both x's with this number. Typing this into our calculator gives us an answer of 6.25. And this is the second coordinate of our point. So we found that our maximum point is 0.5, 6.25, which is precisely what we were asked to show. Let's begin by multiplying out the brackets on the left-hand side. X times 3x is 3x squared. X times minus 4 is minus 4x. 5 times 3x is 15x. And 5 times minus 4 is minus 20. In our other brackets, minus 3 times x squared is minus 3x squared, and minus 3 times plus 2 is minus 6. From here, we can do some simplification. The 3x squared and the minus 3x squared cancel each other off. Minus 4x plus 15x is 11x, and minus 20 minus 6 plus 4 comes out as minus 22. So we end up with 11x minus 22 is equal to 0. We want to solve for x. In other words, we'll want x all by itself on one side of the equation. To do this, we'll need to remove the 11 in front of the x and the minus 22 beside it. The minus 22 represents subtraction. To remove this, we need to do the opposite, which is addition. So here, I'll add 22 to both sides. The 11 in front of the x represents multiplication. To remove this, we'll do the opposite, which is division. So here, I'll divide both sides by 11. Performing the calculation on the right-hand side gives us our final answer. X is equal to 2. The trickiest part of this question is dealing with all the fractions. At its core, a fraction represents division. For example, this x plus 3 below the line represents division by x plus 3. Whenever we have something we don't want in a mathematical equation, we can remove it by doing the opposite operation. Since fractions represent division, we can remove them with multiplication. The x plus 3 beneath the line represents division by x plus 3. So to get rid of this, we should multiply by x plus 3. The x here represents division by x, so to get rid of this, we should multiply by x. And the 2 beneath the line here represents division by 2, so to get rid of this, we should multiply by 2. We can combine all these multiplications into a single step by multiplying across our equation by x plus 3 times x times 2. So let's multiply each of our 3 fractions by this term. Since multiplication is the opposite of division, a bunch of cancellations happen here. In the first fraction, the x plus 3's will cancel. In the second fraction, the x's will cancel. And in our third fraction, the 2's will cancel. This leaves us with a much simpler equation. Now, let's perform some of our multiplications. 5 times x times 2 gives us 10x. X times 2 is 2x, and 3 by 2 is 6. X by x is x squared, and 3 by x is 3x. Now we can multiply out further. Minus 1 times 2x is minus 2x, and minus 1 times plus 6 is minus 6. On the right hand side, 1 times x squared plus 3x simply gives us back x squared plus 3x. On the left hand side we have some simplification. 10x minus 2x is just 8x. Our equation involves an x squared term, x terms, and a number term. We refer to this as a quadratic equation. We can solve this using the quadratic formula, but to do this, we need to group together all the terms on one side and leave a 0 on the other side. Here, let's group our terms on the right. To remove the plus 8x from the left, we'll subtract 8x from both sides, and to remove the minus 6 from the left, we'll add 6 to both sides. Noting that 3x minus 8x is minus 5x, we end up with the equation 0 is equal to x squared minus 5x plus 6. We can solve our equation using the quadratic formula. The first step is to identify our values of a, b, and c. A represents the number in front of the x squared. We just have x squared, which can be thought of as 1 times x squared. So a is equal to 1. B is a number in front of the x, so here b is minus 5. C is a number by itself, so here c is plus 6. Let's sub these values into our formula. We can simplify things here. Minus 5 is plus 5. Minus 5 squared is 25. And 4 times 1 times 6 is 24. Underneath the line, 2 times 1 is just 2. Under the square root, 25 minus 24 is 1. We can simplify further by noting that the square root of 1 is just 1. To deal with the plus minus sign, we split into two cases. In the first, we replace this symbol with a plus, and in the second, we replace it with a minus. To get our solutions to the question, we just have to calculate each of these expressions. 5 plus 1 is 6, so in the first case, we get 6 over 2, which is 3. 5 minus 1 is 4, so in the second case, we get 4 over 2, which is 2. So as our final answer, we've ended up with two solutions to the equation, x equals 3 and x equals 2. We are told that each row has one extra seat compared to the row before it. Row 1 has 28 seats, row 2 has 28 plus 1, which is 29 seats, and row 3 has 29 plus 1, which is 30 seats. To find the number of seats in row 10, we can just continue this pattern all the way down. Row 4 will have 31 seats, row 5 has 32 seats, row 6 has 33, row 7 has 34, row 8 has 35, row 9 has 36, and row 10 has 37. So our answer here is that row 10 has 37 seats. To solve this question, we should try to spot the relationship between the row number and the number of seats. Row 1 has 28 seats. Since we need to add 27 to get from 1 to 28, the number of seats is 27 bigger than the row number. Row 2 has 29 seats. Again, the number of seats is 27 bigger than the row number. The same thing happens for row 3. 3 plus 27 gives us 30, and the same pattern will follow for all the other rows, because each time we increase the row number by 1, we're also increasing the number of seats by 1. So the pattern is that the number of seats is 27 bigger than the row number. We can write this in an equation by saying that seats is equal to row number plus 27. We are told that there's 50 seats in the last row, so we want to find the row number which leads to 50 seats. We can do this by replacing seats by 50 in our equation. So we know that 50 is equal to row number plus 27. To find a row number, all we have to do is subtract 27 from both sides. When we perform the calculation, we find that the row number is equal to 23. So we found that the row number of the last row is 23, therefore there are 23 rows of seats in our theatre. In parts A and B we found the following. Row 1 had 28 seats, row 2 had 29 seats, and row 3 had 30 seats. This pattern continued all the way until the final row, row 23, which had 50 seats. To find the total number of seats, all we'd have to do is add up all these individual values. One way to do this would be to use brute force by getting out our calculator and adding up all these numbers. 28 plus 29 plus 30 plus 31 plus 32, all the way up to 50. However, there's another cleaner approach which uses the result for the sum of an arithmetic sequence. This can be found in the formula book on page 20. It says that for an arithmetic sequence with first term A and common difference D, the sum of the first n terms is given by S of n is equal to n over 2 times 2a plus n minus 1d. If we can find the values of a, d, and n for our sequence, we can use this formula to find our answer. A refers to the first term. In our sequence, the first term is 28, so A is equal to 28. D is the common difference, and this refers to the change needed to get from one term to the next. In our sequence, this change is plus 1, so our common difference is D is equal to 1. Finally, n refers to the number of terms we want to add up. We want to add the values for the first 23 rows, so we have n is equal to 23. So let's take our formula and sub in these values of a, d, and n. 2 times 28 simplifies to 56. And 23 minus 1 times 1 gives us 22. 56 plus 22 is 78. And when we multiply this by 23 over 2, we get our final answer of 897. In part C, we use the sum of an arithmetic sequence formula to find the number of seats in the first 23 rows. To do this, we subbed in the values a equals to 28, d equals to 1, and n equals to 23 into our formula. If we want a general expression for the number of people the first n rows will seat, we can put in our a equals to 28 and d equal to 1, but leave the n as it is. 2 times 28 is 56, and n minus 1 times 1 is just n minus 1. 56 minus 1 is 55, so our expression we get is n over 2 times 55 plus n. So, given any value of n we like, we can sub it into this formula and will tell us how many people the first n rows will seat. This lends itself nicely to the trial and improvement method. Here, we'll make a series of educated guesses until we find the correct answer. We need to find the number of rows to seat 600 people, so we can sub in different values of n until we get close to this target of 600. As a first guess, I'll try n equal to 20. Subbing this into our formula gives us 20 over 2 times 55 plus 20. When we type this in our calculator, we get an answer of 750. This means that the first 20 rows would seat 750 people. We only wanted to sit 600 people, so this number is too high. So for the next guess, it would make sense to try a smaller value of n. Here, I'll try n equal to 15. Subbing this into our formula gives us 15 over 2 times 55 plus 15. Calculating this gives an answer of 525. So we know that the first 15 rows will sit 525 people. Remember, the target is 600 people, so this time we've come out too low. The first 15 rows wouldn't have enough seats for all 600 people. Since this guess was too low, we should try a bigger value of n for our next guess. Let's try n equal to 17. When we sub in and perform the calculation, we get out 612. The target is 600, so our answer here was too high. So we should try a smaller n value for the next guess. Let's try n equal to 16. Subbing in and using our calculator, we get 568. This is lower than the target of 600. We found something interesting here. The first 17 rows would sit 612 people. So the 600 people we have would not be enough to fill these. However, the first 16 rows only contain 568 seats. So the 600 people is enough to fill the first 16 rows. One way to think of this is that with 600 people, we will fill the first 16 rows, but not the 17th. So the value of n we were asked to find is 16. We were also asked to find the number of people who would be seated in the next row. Well, the first 16 rows would sit 568 people, so we'll have 600 minus 568 is equal to 32 people spilling into the next row. To find our total income, we'll need to consider the money we make from selling our adult tickets and the money we make from our children's tickets. Let's start with the adults. Each ticket costs €25, and we sold 276 adult tickets. To find the income here, we simply multiply these numbers together. €25 times 276. This gives us €6,900. For the children, each ticket costs €12. We sold 212 children's tickets, and to find the income from these tickets, we multiply these numbers together. €12 times 212. This gives us €2,544. To find our total income, we'll add together the income from the adult tickets to the income from the children's tickets. This gives us €9,444. The ratio of adult tickets to children's tickets is 3:1. So for some unit, we'll have 3 units for the adult tickets and 1 unit for the children's tickets. We know that the total tickets sold were 752. The total number of units we have here is 3 plus 1, which is 4. The total units must correspond to the total number of tickets, so we'll have 4 units equal to 752. To find what 1 unit is, we can divide both sides by 4. Performing the calculation here tells us that 1 unit is equal to 188. This immediately tells us that the 1 unit we had for the child tickets is equal to 188. For the adult tickets, we had 3 units. If 1 unit is 188, then 3 units will be 188 times 3. This gives us 564 for the adult tickets. So our final answer is we 564 adult tickets sold and 188 child tickets sold. In part FI, we found that there is 564 adult tickets sold and 188 child tickets sold. This information will be crucial when we're tackling this question. We're asked to find the cost of a children's ticket for the show, so let's let X be this unknown value, the price of a child's ticket. We know that an adult ticket costs 2.5 times as much as a children's ticket. So if X is the price of a child's ticket, the price of an adult's ticket will be 2.5 times X. The only other bit of information we're given is that the total income was 17,578. This income will compose of the income from the adult tickets as well as the income from the children's tickets. Let's think about both of these in terms of X. The income from the adults will be the price of an adult ticket times the number of adult tickets. The price of an adult ticket is 2.5x, and the number of adult tickets is 564. Since 2.5 times 564 is 1,410, this comes out as 1,410x. The income from the children will be the price of a child's ticket times the number of child's tickets. The price of a child's ticket is X, and the number of children's tickets is 188. So this comes to 188x. To find our total income, we should add together the income from the adults and the income from the children. So we get 1,410x plus 188x, and this gives us 1,598x for our total income. But remember, we know what the total income is. It's 17,578. We can equate these two expressions to get 1,598x equal to 17,578. To find the value of x, we just need to divide both sides by 1598. Performing the calculation on the right-hand side gives us an answer of 11. This means that x, the price of a child's ticket, is €11. Given any time t in hours, our function c of t tells us how much drug is left in the bloodstream. If we want to know the amount of the drug in the bloodstream after 4 hours, all we have to do is sub in t equal to 4 into our function. In other words, we replace each of the t's with a 4. This gives us minus 4 to the power of 3 plus 4.5 times 4 squared plus 54 times 4. Calculating these gives us minus 64 plus 72 plus 216. Performing this calculation gives us 224 units, which is precisely the answer we wanted to obtain. The top row of our table is labelled with the time t in hours. The bottom row is labelled with our function c of t. To fill in the entries in the second row, all we have to do is take the relevant t value and sub it into our function. In part A, we subbed in t equal to 4 and got an answer of 224. This is the reason that we have a 224 underneath our 4. Completing the table simply requires us to sub in the other t values in a similar way. Our function is that c of t is equal to minus t to the power of 3 plus 4.5t squared plus 54t. Our first blank is underneath t is equal to 2. To find this, we will sub in t equal to 2 into our formula. This gives us minus 2 to the power of 3 plus 4.5 times 2 squared plus 54 times 2. Doing this in our calculator gives us an answer of 118. So this is what we'll write into the box underneath the 2. The next blank is under t is equal to 3, so here let's sub in t equal to 3. This gives us minus 3 to the power of 3 plus 4.5 times 3 squared plus 54 times 3. Doing this in our calculator gives us 175.5, so we'll write this in underneath the 3. Filling in the rest of the blanks will work in a similar way. We just need to sub in t equal to 5, 6, 7, 8 and 9 into our function. Subbing in t equal to 5 gives us an answer of 257.5. Subbing in t equal to 6 gives us an answer of 270. Subbing in t equal to 7 gives us 255.5. Subbing in t equal to 8 gives us 208. And subbing in t equal to 9 gives us 121.5. In part B, we filled out a table. The data here told us the number of units of the drug left in the bloodstream, C of t, at various times t. For example, when t was 0 hours, we had 0 units. When t was 1 hour, we had 57.5 units. And when t was 2 hours, we had 118 units. We have similar information for t is equal to 3, 4, 5, 6, 7, 8 and 9. This data forms 10 pairs. Each of these pairs can be plotted as a point on our graph to give us an idea of the shape of our function. In our graph, the horizontal t-axis represents the time in hours. This corresponds to the first row of our table. The vertical axis is labelled with c of t, the amount of the drug in units. This corresponds to the second row in our table. So let's plot our points. In our first pair, we have t is equal to 0 and c of t is equal to 0. Going to a value of 0 on both axes gives us a point right here. In the second pair, we have t equal to 1 and c of t equal to 57.5. Here, we'll go across to 1 on our t-axis, and up to 57.5 on our C of t axis. This gives us a point right here. In our next pair, t is equal to 2 and C of t is equal to 118. So we go to 2 on our horizontal t axis and up to 118 on the vertical C of t axis. This gives us a point over here. We can perform a similar procedure for the rest of the remaining points. The data in our table gave us 10 points to plot. This gives us a rough structure of the function. To finish our graph, we should join these reference points with a smooth curve. In our graph, the horizontal axis represents the time t in hours, and the vertical axis represents C of t, the amount of the drug left in the bloodstream in units. In part I, we are provided with a time, 3.5 hours. The horizontal axis represents time, and 3.5 is right here. Let's draw up a vertical line and see where this intersects our graph. To find the amount of the drug in the bloodstream, we just need to read off the vertical C of t value for this point. We can do this by drawing a horizontal line across. We get a value of 200. This is our estimation for the amount of the drug in the bloodstream after 3.5 hours. In part II, we are provided with the amount of the drug in the bloodstream. It's 100 units. Our vertical axis represents the amount in units, and 100 units would be right here. Let's draw a horizontal line across to see where this intersects our graph. To find the time it takes for there to be 100 units of the drug in the bloodstream, we should drop a vertical line down and read off the value from our time axis. The value here is approximately 1.7. So our answer is 1.7 hours. We need to find the rate at which the drug amount is changing. A key point to keep in mind here is that the rate of change is obtained by differentiating our function. At its core, this is what differentiating does. It tells us the rate of change. So whenever we see the phrase rate of change in a question, alarm bells should go off and we should think about differentiation. Our function is C of t is equal to minus t to the power of 3 plus 4.5 t squared plus 54t. To find our rate of change, we just need to differentiate this. Whenever we're adding or subtracting terms, we can differentiate each term individually. So we can tackle the three components here separately. First, let's focus on the minus t to the power of 3. To differentiate this, we can use our rule for differentiating powers. We multiply down by the power, then reduce the power by 1. Here, the power is 3, so we'll multiply down by 3, and then we'll reduce the power from 3 to 2. So we get minus 3t to the power of 2. We can use the same strategy to differentiate the 4.5t squared. Here, the power is 2, so we'll multiply down by 2, and then reduce the power from 2 to 1. 4.5 times 2 gives us 9, and t to the 1 can just be written as t, so this gives us 9t. Finally, let's tackle the 54t. There's a useful fact which says that for any constant k times t simply differentiates to k. In other words, if you have a number being multiplied by t, it just differentiates to the number. Applying that here, 54t will just differentiate to 54. So our final answer here is that the rate of change of our function, c dashed of t, is equal to minus 3t squared plus 9t plus 54. In part EI, we found the derivative of our function, c dashed of t is equal to minus 3t squared plus 9t plus 54. This derivative represents the rate of change of our function. We're asked to find the rate of change after 4 hours. Since t represents time in hours, all we'll have to do here is sub in t equal to 4 into our derivative function. This gives us minus 3 times 4 squared plus 9 times 4 plus 54. This simplifies to minus 48 plus 36 plus 54. Performing this calculation gives us our final answer of 42 units per hour. We need to find the maximum amount of the drug in the bloodstream. To find the minimum or maximum of a function, we can follow these steps. First, we differentiate the function. Then we'll set the derivative equal to 0 and solve. And finally, we'll sub back into the original function. The original function we were given was c of t is equal to minus t to the power of 3 plus 4.5t squared plus 54t. The first step would be to differentiate this function, but this is something we already did in part EI. Here, we found that the derivative, c dashed of t, is equal to minus 3t squared plus 9t plus 54. The second step is to create an equation by setting this derivative equal to 0. Our equation involves a t squared term, a t term, and a number term. This is referred to as a quadratic equation, and it can be solved using the quadratic formula. This tells us how to find the roots of a quadratic ax squared plus bx plus c is equal to 0. This is similar to the form our equation is in, but we should note that we have t playing the role of the x. To use our formula, we'll first need to identify the values of a, b, and c. A will be the number in front of the t squared, which here is minus 3. B is the number in front of the t, and here b is equal to 9. C is the number all by itself, so here c is equal to 54. Let's sub these values into our formula. we can simplify things a bit here. 9 squared is equal to 81. Minus 4 times minus 3 times 54 is plus 648. And 2 times minus 3 is minus 6. Under the square root, 81 plus 648 gives us 729. As it turns out, if we type root 729 into our calculator, we get a nice whole number. It's 27. From here, we need to deal with the plus-minus sign. This symbol means that we need to split into two cases. In the first, we replace the symbol with a plus, and in the second, we replace this symbol with a minus. In our first case, minus 9 plus 27 all over minus 6 comes out as minus 3. In the second case, minus 9 minus 27 all over minus 6 gives us plus 6. So we've ended up with two values of t. But remember, t represents a time in hours. In this context, a negative value of t doesn't really make sense. So we can rule out the t equals minus 3 and focus on the t equal to 6 moving forward. The interpretation here is that the drug amount will be maximised after 6 hours. However, we weren't asked to find the time when the drug amount is maximised. We wanted to find the actual amount of the drug at this time. To find this, all we have to do is sub in this t equal to 6 back into our original function c of t. C of t is equal to minus t to the 3 plus 4.5t squared plus 54t. To sub in t equal to 6, we just replace each of the t's with 6. This gives us minus 6 to the power of 3 plus 4.5 times 6 squared plus 54 times 6. This simplifies to minus 216 plus 162 plus 324. Performing this calculation gives us our final answer of 270 units. We need to show that the drug amount is decreasing after 7 hours. A key point to keep in mind here is the following. A positive rate of change means that the function is increasing, whereas a negative rate of change means that the function is decreasing. So to demonstrate that the function is decreasing, we just need to show that the rate of change is negative. Well, we've seen before that our derivative tells us the rate of change. And in part EI, we found our derivative. C dash of t is equal to minus 3t squared plus 9t plus 54. We are asked to consider a timing of 7 hours after the drug is taken. To find the rate of change at this time, all we have to do is sub in t equal to 7 into our derivative. This gives us minus 3 times 7 squared plus 9 times 7 plus 54. This simplifies to minus 147 plus 63 plus 54. Doing this calculation gives us an answer of minus 30 units per hour. The crucial thing to note here is that this rate of change is negative. So at t equal to 7, the rate of change is negative. Hence we can conclude that the drug amount is decreasing at this time. We need to find s, the speed of the tsunami. We can find this using the given formula. s is equal to the square root of g times d. To use this, we'll need to identify the values of g and d. G is given to us directly. It's 9.8. D is the depth of the ocean in meters. We're told that we have a depth of 2,000 meters, so D is going to be 2,000. Subbing these values in, we get the square root of 9.8 times 2,000. Typing this in our calculator gives us our final answer of 140. And the units here are meters per second. We need to find the time it takes the tsunami to reach land. The distance, speed, time triangle is useful here. Whichever quantity we want to find, we cross this out and the triangle will tell us the formula to find it. We need to find the time. Crossing this out in our triangle leaves distance over speed. So our formula is time is equal to distance over speed. Let's try to find both these values. For the distance, we're told that our tsunami begins 400 kilometers from land. We'll need to be careful with our units here. The speed of the tsunami is measured in meters per second, so it'll be a good idea to convert this distance to meters as well. 1 kilometre is equal to 1,000 meters. So to convert from kilometers to meters, all we need to do is multiply by 1,000. This means that 400 kilometers is equal to 400,000 meters. So this is our value for the distance. Now, let's think about the speed. In part I, we found that when the depth is 2,000 meters, the speed of the tsunami is 140 meters per second. Since we also have a depth of 2,000 meters in part II, we can use this calculation we had earlier. Our speed is going to be 140. So, distance over speed is 400,000 over 140. This comes out as 2,857.1429. Since our speed is in meters per second, the unit here will be seconds. However, we need to give our answer correct to the nearest minute. To convert from seconds to minutes, we divide by 60. This comes out as 47.6190 minutes. We want our answer correct to the nearest minute, so to get our final answer, we should round this off to 48 minutes. The formula we are given is S is equal to the square root of G times D. To rearrange this formula to give D in terms of G and S, we need to isolate the D all by itself on one side of the equation. In other words, we need to end up in the form D is equal to something. The D appears on the right-hand side, and there's quite a few things going on around it. It's being multiplied by G, and all of this is under a square root. To isolate the D, we'll need to get rid of the square root, and we'll need to get rid of the G. When we're removing things, a good principle is to start from the outside and work your way in. The outermost layer here is the square root, so this is what we should target first. To get rid of something in an equation, we should perform the inverse or opposite operation to both sides. The opposite of a square root is a square, so here let's square both sides of our equation. The square root will cancel with the square, so we end up with s squared is equal to g times d. Now let's get rid of the g. This is being multiplied by the d. To get rid of it, we should do the opposite, which is division. So the next step is to divide both sides by g. Multiplication by g will cancel with the division by g, so we end up with a final answer of d being equal to s squared over g. We need to find the depth of the ocean d. In part I, we found a formula to calculate d. d is equal to s squared over g. Once we identify the values of s and g, we can sub into this formula to get our answer. S represents the speed of the tsunami in meters per second. We're told that the speed is 55 meters per second, so S is equal to 55. G is given to us directly in the question. G is equal to 9.8. Subbing in these values, we get D equal to 55 squared divided by 9.8. Putting this in our calculator gives us 308.6735. We need to give our answer correct to the nearest meter. So rounding this off, we get our final answer that the depth, D, is equal to 309 meters.